Hey, welcome to the Matrix. This is where Keanu Reeves lives. If you get that joke, then you are awesome. Anyway, so we just made pyruvate in glycolysis, and so pyruvate is going to travel into the matrix of the mitochondria, so deep inside, right? Now, first we have this little junction step, this intermediate step before the citric acid cycle or Krebs cycle. So let's look at the summary and then let's fill in what's going on over here. So the summary is that we need to convert pyruvate, which is a 3-carbon molecule, into acetyl-CoA, and that's a 2-carbon molecule. Acetyl-CoA is what actually enters into the Krebs cycle, and it joins with a 4-carbon molecule known as oxaloacetate. So when a 2-carbon and a 4-carbon smush together, we get a 6-carbon molecule known as citrate or citric acid, and that's where the name of this comes from. So the citric acid cycle is going to progressively pull off electrons, make a little bit of ATP, but the main goal is to generate or pull those electrons off. And so we're going to talk about those electron carriers a little bit here, okay? This step, the matrix reactions, this is where carbon dioxide gets released as a waste product. So in our overall equation for cellular respiration, we know that glucose and oxygen comes in, and we know that carbon dioxide and water come out. So we just talked about what the purpose of glucose is, but we haven't yet talked about oxygen. Here's where carbon dioxide comes in, and then we'll talk about water. So that's going to be in the next step. So let's start with our steps over here. So pyruvate comes in, and that's what actually goes into this first box. It's a 3-carbon molecule, right? And the addition of coenzyme A, that's what CoA is short for, will join up, and then we go to a 2-carbon. So when you go from 3 carbons to 2 carbons, that means a carbon dioxide has been released. Again, we are condensing a lot of steps to try to make things simpler, right? All right, so 2-carbon plus 4-carbon join up, and we get a 6-carbon molecule known as citrate or citric acid, okay? Now, the 6-carbon goes to a 5-carbon, so that means that carbon dioxide must have been released. And then over here, I drew my little electron carrier, NAD+, zooms in, picks up a couple of electrons here, and becomes NADH. All right, and after that, we come over here to this alpha ketoglutarate, this 5-carbon molecule, but remember my little starburst? That means that we're going to use some energy to charge up ADP and build ATP, right? Here I've got 2 NAD+. Empty electron carriers are going to pick up some electrons and become NADH. And making his first appearance is FAD. It's another electron carrier, and when he picks up his electrons, he becomes FADH2. And so at that point then, oh my gosh, I forgot my carbon dioxide. So here comes a 5-carbon to a 4-carbon. That means a CO2 was released. So this is the citric acid cycle, also known as Krebs. I tend to say Krebs because it's fewer syllables and easier to say. Okay, coming back with my highlighter. So remember, 2 NADH are created here. I've got 1 over here. So that's a total of 3 NADH so far. All right. Let's use blue to track carbon dioxide. Typically, we're not really that concerned about how much CO2 is produced just because it's considered a waste product, but it is a product, so we'll go ahead and identify that as well. I have 1 little ATP that is made, and then what color should we use for FADH2? Let's use this light purple color. How about that? Okay. So, if we come over here and we're looking at these electron carriers, if you think of oil rig, don't panic. We're not going to do anything crazy with redox reactions, but the general idea is that electrons can be picked up, shuttled around, moved back and forth between molecules, right? So in this case, when NAD+, when this molecule does not have any electrons, okay, that is the form that it takes. We call it NAD+. When it picks up these electrons, it's still like the same molecules, like a little taxi cab, but now he's got passengers. He's got 2 electrons on there, so he's called NADH, okay? So remember, rig means reduced is gained. So NADH is the reduced version of the electron carrier, right? So again, they're like pretty much the same thing. They're just a little bit different. An empty taxi cab, an occupied taxi cab. And where do you think these taxi cabs are going to take their electrons? Why, to the electron transport chain, of course. So the whole purpose of these matrix reactions is to just pull electrons off of all of these molecules, because that is what is going to power the electron transport chain. So that becomes really, 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 really important. Okay, so here we've got our summary. Here we've got everything drawn out that we need to know. We got a reference point. And then again, if you want to go back in and make it a little bit prettier and color code certain things, go for it, friends. All right, next step, the electron transport chain.